I'm sorry, did it begin? I don't think I can see it when I'm in my presenting mode.
It is recording.
Okay, thank you. All right, well, hello, my name is Alice Shree, and I'm from Amity Regional High School. My project this year was determining the effect of climate change on future winter lipid and carbohydrate consumption of Connecticut wood frogs, whose scientific name is Rana sylvatica. Climate change, defined as significant variation in weather patterns, has been shown to have adverse effects on the habitats of many species. One such is the sumibium, an extensive microhabitat located underneath the snow where many species in the northern temperate areas spend the winter season. It provides a relatively warm and stable microclimate compared to above ground habitats. However, the threat of a warming Earth that is brought on by climate change has the potential to lead to diminished or varied snow and ice cover, and this can therefore lead to changes in the ecology and distribution of winter-adapted species. This threat is of particularly great concern for amphibious ectotherms because their body temperature is closely tied to the temperature of their environment, and they have relatively limited dispersal abilities. Wood frogs are freeze-tolerant, subniveum-dwelling amphibians whose habitats range from Alaska to the southern Appalachian Mountains. They're pictured in the photo on the right. During the winter, they are able to freeze up to two-thirds of their body's extracellular water content, and they're reported to freeze at temperatures below negative 1.6 degrees Celsius and to thaw at temperatures above negative 0.16 degrees Celsius. Before freezing, wood frogs use lipids as their main energy source, and during the freezing and thawing process, their metabolism is fueled mainly by carbohydrates. As shallow-burrowing animals, they will be among the first to be affected by variable snow cover. Environmental temperature can have consequences for energy requirements, and it may even increase the risk of lethal freezing. They depend on the remnants of body reserves from the fall season to provide them with energy for breeding in the spring, and consequently, their survival and reproductive success is closely tied to climate-influenced winter energy requirements. Cryoprotectants are important substances that are used to help them survive freezing, with various purposes including controlling internal ice formation and mitigating the effects of cellular desiccation. The production and distribution of these cryoprotectants have energetic costs, however. Given the possibility of increased exposure to cold temperatures, climate change can increase the risk of reaching lethal ice contents. In addition, because freeze-thaw cycles require energy to complete, greater instability in environmental temperatures can heighten energy demands, depleting energy sources and cryoprotectant stores. It's important to look into this topic in different regions of the wood frog's range because different regions have differences in snow cover, meaning there's a potential for varied regional effects and outcomes for overwintering wood frogs. The purpose of this project was to determine the effect of climate change on future winter lipid and carbohydrate consumption of Connecticut wood frogs. The independent variable was future climate change scenarios for the years 2030, 2070, and 2080, and the dependent variable was the metabolic cost as determined by lipid and carbohydrate consumption required for a Connecticut wood frog to survive one winter. The control was the present-day lipid and carbohydrate consumption of these wood frogs. It was hypothesized that climate conditions in the future would increase the winter lipid and carbohydrate consumption of Connecticut wood frogs. Wood frogs use cryoprotectants to control internal ice formation, prevent intracellular freezing, and perform other processes, and the production and distribution of these cryoprotectants have energetic costs. Since warming and sporadic weather caused by climate change threatens the synovium and may lead to more freeze-thaw events, more energy would be needed by the frog to survive through the winter. To test this hypothesis, data collected on Connecticut wood frogs' hypernacular temperature that was applied by the mentor was cleaned. Data consisted of temperatures from three stations, air, surface, and soil, and temperature was collected at two different locations in Connecticut with three sites per location over the winter seasons of 2020 to 2023. Data was cleaned to restrict the time frame to be between November 1st and April 15th, which is the defined winter season for frogs and the period during which they hibernate, and also to organize it. All the data was combined into a master file. To calculate present-day energy expenditure, the software RStudio was used to plot each location, site, station year, combinations data as date time against its respective temperature reading. Lines representing the minimum, maximum, and average temperatures were included on the graphs. RStudio was then used to calculate the number of times the minimum temperatures fell below negative 1.6 degrees Celsius, then above negative 0.16 degrees Celsius over the course of the winter period, and each of these instances represented a freeze-thaw event. In the picture, I had instructed our studio to find the number of times the temperature fell below negative 1.6 degrees Celsius and then above negative 0.16 degrees Celsius for the site called Westford during the winter of 2021 to 2022. The amount of lipids and carbohydrates required for a wood frog of average mass to complete one freeze-thaw cycle was obtained from the literature and then multiplied by the number of freeze-thaw cycles a wood frog would complete over the course of one winter. The energy costs for each of the 3 years were averaged to find the estimated present energy expenditure of Connecticut wood frogs to survive a single winter. To predict future lipid and carbohydrate consumption, Niche Mapper was used to simulate wintering wood frogs in future microclimate conditions for the years 2030, 2070, and 2080. Average energy expenditures for each future year were determined based on the predicted number of freeze-thaw events and the current lipid and carbohydrate needs per freeze-thaw cycle. Model accuracies were validated, and the average energy consumption of a Connecticut wood frog over the course of one winter was compared to the calculated present-day consumption. Throughout the project, my mentor provided guidance and instruction. Modeling at such a fine scale proves sort of difficult, so I need to push back my timeline in terms of modeling the number of future years I had planned for. Results thus far, however, project that over the course of one winter, Connecticut wood frogs will undergo a fewer number of freeze-thaw events in 2030 as compared to present day. During the present day, wood frogs were projected to undergo between 3.6 and 6 freeze-thaw cycles, while in 2030 they were projected to undergo between 2 and 3 freeze-thaw cycles, as seen in Figure 1. This result was extremely statistically significant with a p-value of 0.0007. These plots made in RStudio display the projected temperatures of each of the sites studied for the year 2030. You can visually see the instances when the blue lines, which represent minimum temperature, fall below negative 1.6 degrees Celsius, and then above negative 0.16 degrees Celsius, which are the dotted lines. On this slide, I have pasted Figure 2 from the previous slide again, which displayed projected temperature data for the site Bailey Trail in the year 2030, and included the temperature data for Bailey Trail during the winter of 2021 to 2022, which is Figure 8. And you can visually see how the minimum temperature falls below negative 1.6 degrees Celsius and then above negative 0.16 degrees Celsius more times in the 2021 to 2022 graph than the projected 2030 one. Results thus far project that Connecticut wood frogs' lipid consumption during the winter will be lower in 2030 as compared to present day. During the present day winter, Connecticut wood frogs were projected to use 0.0002713 milligrams to 0.000444 milligrams of lipids per gram of frog, and in 2030 they were projected to use 0.00148 milligrams to 0.00222 milligrams of lipids per gram of frog, as seen in Figure 9, and this result was also extremely statistically significant with a p-value of 0.0003. Results also project that over the course of one winter, Connecticut wood frogs' carbohydrate consumption will be lower in 2030 as compared to present day. During the present day winter, they were projected to use between about 0.7 to about 1.13 milligrams of carbohydrates per gram of frog, and in 2030, they were projected to use about 0.38 to about 0.6 milligrams of carbohydrates per gram of frog over one winter, as seen in Figure 10, a result which was also extremely statistically significant with a p-value of 0.0003. To reiterate, the purpose of this project was to determine the effect of climate change on future winter lipid and carbohydrate consumption of Connecticut wood frogs. It was hypothesized that climate conditions in the future would increase the future winter lipid and carbohydrate consumption of these wood frogs, and as projections support decreased lipid and carbohydrate consumption for future years as compared to present day, which was seen in Figure 1, results thus far do not support this hypothesis. This decrease in needed lipid and carbohydrate consumption projected for future years may be due to the fact that a lower amount of the cryoprotectants which prevent intercellular ice formation and dehydration during freezing would be needed, seeing as projections predict fewer freeze-thaw events in the future. This would lead to Connecticut wood frogs needing to produce and distribute a lower amount of cryoprotectants, allowing for a decrease in necessary lipid and carbohydrate amounts to sustain freeze-thaw cycles throughout the winter. Additionally, though climate change has been shown to result in more erratic, unstable weather patterns, overall it has shown to produce increased temperatures and to decrease the length of the winter season, as defined by being the first to last day with soil frost. If the temperature falls below negative 1.6 Celsius, the identified threshold for freezing, fewer times in the future than during the present day, whether that is in the context of increased temperatures during the winter or a shortened winter season, a lower number of freeze-thaw events would occur. This would lead to an overall decrease in the amount of lipids and carbohydrates needed in total to undergo freeze-thaw events throughout the winter. These
Alice, you have
explanations
about
could
2 minutes.
offset the potential effects.
You have
Yes?
about 2 minutes left.
Okay, thank you. Thank you. These explanations could offset the potential effects that a more unstable or less substantial synovium could have on Connecticut wood frogs' winter lipid and carbohydrate needs. However, since Connecticut wood frogs are projected to experience a fewer number of freeze-thaw cycles, they may end up spending more time in a non-frozen state. And during this time, until ice nucleation, even at sub-zero temperatures, they are still metabolically active. Therefore, they would be unable to experience the benefits of a slower metabolic rate that freezing offers. Furthermore, in the event that soil temperatures rise too quickly, Connecticut wood frogs will also be forced to undergo physical stress by their environment being too unpredictably warm, which can also have adverse effects, especially since as amphibians, their metabolic rates are dependent on stable temperatures and they are hindered by their relatively limited dispersal capacities. Increased temperatures due to climate change could also, even if meeting lowered energy demands during the winter season, lead to heightened energy demands or further complications in other seasons. It should be noted that all results are predictions based on estimates of lipid and carbohydrate consumption in future climate scenarios, so they are therefore not definite, and energy consumption as a result of freeze-thaw events is only one element of a Connecticut wood frog's energy needs to survive throughout the winter. In addition to this project could be to quantify the resting metabolic rate of a Connecticut wood frog during the winter when they're unfrozen, so that in conjunction with energy requirements while frozen, a detailed energy budget for current and future winters could be estimated. Also, all freeze-thaw events were assumed to require the same amount of lipid and carbohydrate consumption, but freeze-thaw events of varied lengths may also have varied energy requirements. So next steps to this project could be to quantify the duration of each freeze-thaw event a wood frog might undergo and to examine the number of days per winter that these wood frogs are metabolically active. The results of this project can provide insights into the potential effects of climate change on wood frogs' necessary cost to survive future winters, specifically in the Connecticut region, as well as provide information on how certain habitats may become unsuitable for wood frogs in the face of a changing climate. It can
Alice,
also
your
provide
time is up.
information. Okay, thank you so much. Should I go back to the main screen and stop sharing my screen, or just stay here?